Okay, another learning rule, number 3, which is the Hebbian learning rule, introduced by Dr. Hebb. So Hebb in 1949 stated the following, stated his learning rule as follows. So when an axon of cell A is near enough to excite a cell B and repeatedly, so you have some sort of frequency, or persistently, continuously, takes place in firing it, some growth process or metabolic change takes place in one or both cells such that A's efficiency as one of the cells firing B is increased. So A is more efficient at firing cell B. In other words, if two neurons, A and B, on either side of a synapse or connection are activated simultaneously, meaning synchronously, then the strength of that synapse is increased. And this rule is often supplemented by the follow. If two neurons, A and B, on either side of a synapse are activated not at the same time, asynchronously, then that synapse is selectively weakened. So it is reduced or even eliminated, so that chance coincidences do not build up connection strength. So there is no, so you eliminate it so that there is no coincidence that it builds up. So Hebbian learning rule, it's a purely feed-forward, because you have, just like when we saw A and B, and supervised learning rule, you don't have any supervisor. The learning signal is equal to the neuron's output. Remember our general learning rule, delta Wi equals C times the R signal times X. So our R signal in this case is purely the neuron's output, which is given by this formula. So you have the input vector weighted and activation function, okay? This is for the weight vector. If the weight for the weight for node I, which is coming from input J or Xj, in this case, you just replace this formula. Instead of having vector X, you just put Xj. The weight initialization at small random values around Wi prior to learning. So this is how you use the Hebb learning rule. If the cross product of the, sorry, look at that. If the cross product of the output and input, or the correlation, is positive, you have an increase of the weight. Your delta W would be positive, and then you would increase the weight. The new weight would become bigger than the previous weight. Otherwise, the weight decreases. And this can be seen as the output is strengthened in turn for each input presented. So every time you present that input, your output would be strengthened. So on that basis, the frequent input patterns will have more influence at the neuron's weight vector and will eventually produce the largest output. That's why Hebb mentioned that repeatedly. So there is a frequency here. So the most frequent ones. And in fact, if this is your input, this is your current weight, W, the W. So W prime is W plus delta W, okay? So you'll have here an increase in the weight. And then here, you have a decrease in the weight. Yeah, so W transpose X is less than W transpose X. So in some cases, the Hebbian rule needs to be modified to counteract and constrain growth of weight values, because the more frequently you have an input, the more your weight increases. So you would need to modify it to, so it's going to be saturated. So it's going to have an unconstrained growth of weight values, which takes place when excitations and responses consistently agree in sign. So in that case, you would need to do something, and this corresponds to the Hebbian learning rule with saturation of the weight at a certain preset level. So what you do is every time the weights reach a certain preset threshold, you saturate. You don't increase the weight anymore. Okay, so because of this effect here. So single layer network with Hebb learning rule of a set of input-output training vector is called the HebbNet. So if you have a single layer network, which is trained with the Hebb learning rule, you call it the HebbNet. So we recap. So if two neurons of a connection are activated simultaneously, synchronously, then the strength is increased. Then the strength of that connection is increased. If they're activated not at the same time, asynchronously, then the strength is weakened or eliminated. So the Hebbian synapse is time dependent. It depends on the exact time of occurrence of the two signals. It is local. Locally available information is used. You don't go very far. And interactive mechanism, so learning is done by two signal interaction. That's why it's interactive. It's conjunctional or correlation mechanism, co-occurrence of two signal. And the Hebbian learning rule is found in the hippocampus, in part of the human brain, which is or animal brain, which is the presynaptic and the post. So you talk here about presynaptic and postsynaptic weights. A special case of the Hebb learning rule is the correlation learning rule, which is a supervised learning applicable for recording data in memory networks. So you have some sort of here memory with binary response neurons. And in this case, your learning signal R in our generalized learning rule is a desired output, DI. That's why you kind of have some memory here. Same rule. So if this is the input vector, if you're talking about the Jade input, so you just replace X by XJ. So a special case of the Hebbian learning rule with a binary activation function and for the output equal to a desired input. The weight initialization at small random values around WI equals 0 prior to learning, just like the Hebb learning rule. And the same vectorial diagram applies. Thank you.